I'm CP Srinivasan and this is my concept video presentation for Exam 3 project, Entropy and Battleship. This is a project that combines a classic childhood game with advanced information theory. Many of us have played Battleship before. Usually we play by feeling or guessing randomly, but in this project I try to replace luck with math by using the concepts of entropy and mutual information to find the ships in the most efficient way possible. First, let's look at the setup. To make this mathematical, I had to define the rules clearly. For this model, I am using a 5x5 grid. Hidden somewhere on this grid are 3 ships and each ship has a size of 3 units. This specific setup is very important. Because the grid is small and finite, it allows us to define a state space, which we can call S. The state space is just a list of every single possible way we could place those ships on the board. Unlike the real world where the possibilities may seem infinite, here we can actually count every valid configuration. Once we have our state space, we can calculate the initial entropy. At the very start of the game, the board is blank. We have 0 clues. This means that every single valid board configuration is equally likely to be the secret answer. This is, in probability terms, this is a uniform distribution. When we have a uniform distribution, calculating the entropy is easy and straightforward. We use the formula highlighted over here, h of s equal to log base 2 to the size of s. This number gives us our baseline uncertainty. It represents exactly how many bits of information we need to solve the game. Our goal throughout this project is basically to drive this number down to 0. Now let's look at how I translated these definitions into Python code. I created a class called Entropy Engine to handle the heavy lifting. There are 3 concepts here. The random variable s in this code represents the hidden true arrangement of the ships. This is the unknown we are trying to find. The state space omega in my code is stored in the list self.allValidBoards. This list contains every single possible valid placement of those ships in the board. The current state space S, which is S prime, this is the self.current possible boards. As we play and get hits or misses, we remove impossible boards from this list. To generate this list, I use the Python itotools.combinations function. This acts like a filter, ensuring we only keep the board states where the ships do not overlap. This forms our basic initial probability distribution. Now, the second function is the calculate entropy function. Once the game starts, we need to calculate the entropy after every turn. Here we can see the general entropy formula. However, because we are maintaining a uniform distribution here, as every board configuration is equally likely, we don't need to run like this complex summation loop every single time. We can simplify the math in the code basically to just the log base 2 of the length of s prime pointed to the simplified formula in the previous slide. So if there are 100 possible boards left, the entropy is just log 2 of 100. This makes the computation very fast and accurate. And one of the most critical functions in this code is the update entropy state function. This is used for filtering, and this is where the learning happens. Every time we take a shot, we get an observation called X. This observation is either a hit or a miss. The code takes this new fact and performs a filtering operation over here. It looks at the current list of possible boards and deletes any board that contradicts the new evidence. If we missed at A1 or 1,1 basically, we delete every board that had a ship at 1,1. If we make a hit at A1 at 1,1, we delete every board that didn't have a ship at 1,1. This leaves us with a new smaller set of possibilities, S prime new, thus lowering our entropy. So we can calculate entropy, but how do we win? This brings us the best strategy, maximizing information gain, which is the part B of our project question. We use the concept of mutual information over here. Mutual information measures how much knowing one variable, like a specific grid cell, reduces the uncertainty about the other variable, the location of the ships. My strategy here is simple. always guess the cell that has a 50% probability of being hit. Why 50%? We know that the properties of a binomial random variable, shown here, that maximum binary entropy occurs when p equal to 0.5. This is something we calculated in class 2. If I shoot at a spot that is like 99% likely to be a hit or even a miss, I learn absolutely nothing new because I already know that it's going to be hit or a miss. However, if I shoot at a spot that is at the probability of 50-50, I can easily eliminate roughly half of the remaining possibilities and possible vote configurations. This ensures that the fastest reduction in uncertainty happens. So finally, in conclusion, this project shows how we can transform a battleship from a game of blind guessing into a process of calculation. By strictly defining our state space and using entropy as a guide, the computer doesn't need luck. It simply asks the question that provides the most mutual information. This is a direct application of the theory we learned in class. It demonstrates that entropy is just a theoretical concept. It is a tool we can use to optimize search strategies in complex systems. Thank you for your time and hope you enjoyed the mathematics behind my game. Please try out the demo, and if you want to know more information, refer the demo video attached earlier. Thank you and have a good day.